So thank you, everybody. So I'm going to be presenting today on some work that's been going on with the Galleries to Calories project at Edinburgh. I should say, despite the title slide just saying me, this has been a largely a team effort, but there's too many names to fit on the slide. So I would probably just say a big thanks to my colleagues at Town Rock who have been instrumental in helping getting the field data in that underpins most of this talk. So to sort of set up, for those who don't know what the Galleries to Calories project is, it's looking at a sort of pilot heat storage project in flooded mine workings within the Midlothian coalfield. And this talk is somewhat of a follow-on from some work I presented last year at the London Geothermal Symposium, where we looked at sort of a regional scale coalfield, its set of interactions and hydrological processes between the coalfield and surface water courses. So the work I'm going to try and present today is sort of a zoomed in look at that and actually sort of say, right, how does our local study in the geobattery area interact with the coalfield? So really, there's two questions I'm going to address with here, and that is obviously the local scale interaction with the wider coalfield, and then the second question I want to sort of try and touch on is, from what we've learned, is there any way we can use this to potentially try and assess any leakage or sort of any perturbations to the system were this to be an operational scheme in the long run? So on a regional scale, this is sort of a summary from it, but what we had initially done was sort of conduct a regional mass balance on mining related pollutants, so things like iron and manganese across the coalfields, try and work out where they are sort of currently entering the system. This was using historic SEPA data. And the take home is this is at low flow conditions, so sort of 95 exceedance probability. And we find that from the headwaters, you've got about 20 kilograms of iron coming into the top of the catchment at the first gauging point. And then even though there are some faults through some of the stratigraphy and a few shallow workings that aren't necessarily named to just exist, there's surprisingly not much of a net addition to the system. But then once we get into the coalfield proper, which is where our geobattery is sited, we suddenly find that there's a net contribution of 103 kilograms a day of total iron across a fairly large section of the coalfield. And the question is, well, how, on a more granular basis, where does that where does that contribution come from? And one of the big unknowns on the local school is this watercourse called the Bilston Burn, which flows over the top of the geobattery. So as you say here, before the geobattery comes in, which is in the red box, we've not had much net change along that blue section of the river. Then for context of what comes, the watercourses that I'm now covering here are the Bilston Burn here, and then the Kilburn slightly to the south, and then they join up and then join the North Esk down here. And this is what we want to understand, what's going on. And then once we leave the section at Iron Mills Park in Dalkeith, we've still got quite a significant amount of iron in the system. So how have we gone about doing this? So we've sort of undertaken a sort of fairly intensive physiochemical program. So in the map here, we've sort of got all the sampling points that we've done in yellow circles, and then there's SEPA flow gauging stations in the yellow triangles. But largely, we've had sort of up to 36 localities at the peak of the program, where we've sort of been taking sort of fairly standard physiochemical measurements to try and build up a picture in time how this system behaves. And then that's also been coupled with a slightly less intensive, although still a large amount of samples of sort of actual dissolved elemental chemistry as well. So the last thing I'm going to sort of quickly talk on though about is to build all this is we need to sort of understand how the flow in the rivers is behaving. And one of the sort of simple ways we can do this is sort of assume that where you haven't got a flow gauge, the flow at that point is going to be proportional to the area of the catchment at that ungaged point relative to a gauged point. For those, I'm not really going to go into massive, but you can sort of validate this through assuming that the catchment behaves as a linear reservoir, which basically means flow is proportional to its volume. So, but the sort of take home of this is if that conceptualization of the catchment is true, then the sort of mass flux of a conservative tracer like chloride should scale with the catchment area. So we were able to validate this across different flow conditions for known gauge points, which are the solid circles, and then we used that assumption to predict what it would be at ungauged points, and we find that the model that sort of area scaling relationship seems to be a valid approach for doing this in the Midlothian basin. So this provides us a tool to sort of start getting flow data where we don't necessarily have long-term flow measurements actually at that site. So the two things we want to use that for in terms of the local hydrological understanding is to sort of, how are these contribution to the overall discharge of the system, and how are they interacting with their local underlying geology? In other words, what's their base flow contribution? So there are sort of two burns that we're interested in. So the Bilston's the main one, but then the Glencorse is upstream as a sort of control before the Coalfield is entered. And what we're going to use is we can use a conservation of mass-based idea using electrical conductivity, because that is proportional to total dissolved solids, which on small length scales we can effectively assume is conservative. It isn't on large scales, but when it's 100 meters, we're going to assume it's a conservative process. And this allows us to get a relationship for the discharge. If we know what it is at the point on the ESC, which we can get from the area scaling, we can predict the discharge elsewhere from the measured conductivity readings. And these are the scaled discharge relationships. And then just some areas of the solid pinks, the area we used, and then the pale pinks, the catchment that we're predicting. Two cases there for you. And when we run this, we sort of obviously can do this on a seasonal basis, and we can get the BB09 is effectively just the downstream Bilston burn gauging point that we did in the baseline study. But what we find really is over the year, the Bilston is contributing to about up to 10% of the flow in the North Esk downstream of that point. So that's sort of a constraint on the fluid flow out of there. And then similarly for the Glencorse upstream, that's contributing potentially up to half of the water downstream of its confluence. But that one, the variability in that can be attributed to the fact that there's a reservoir at the top of it. So we've sort of looked at fluid contributions to the system and their but what about their sort of wider interactions? So in terms of how do we look at base flow? I mean, you can use the same mass balance argument where you've got either water coming in from rainfall runoff, water in from the subsurface, and then that adds together to give you the mass going down the river. So to constrain these end members, we can sort of say, right, the electrical conductivity of runoff, we take that as the median rainfall conductivity from the Auchencorth Moss monitoring station, which is just south of Edinburgh. And then for the base flow conductivity, we basically say, well, what's the maximum conductivity we observe? And then just to account for the fact that we don't necessarily observe the global maximum, we kind of just add 5% to that. And then that allows us to work out our base flow fractions from our observed conductivity in that catchment. So if we do this for the Bilston, we can find that it's sort of obviously seasonally variable, but it's sort of staying somewhere between 40% and maybe just over 90% of its flow comes from subsurface rather than direct runoff. And there's a sort of fairly climbing probability density function, cumulative probability function for that. So it does vary quite a lot throughout the year. But if we compare that to the Glencorse, that exceedance probability is actually fairly flat as a signal. So you actually get a fairly constant base flow contribution in that river compared to the Bilston. So, but it also, as you'll see in a minute, has a slightly lower average contribution, so it's slightly less connected to its underlying geology. And then the final one is the Kilburn, which joins the Bilston. And that one, again, has got fairly uniform behavior, but it's even higher than the Bilston. So this one's kind of potentially 80% base flow fled most of the time. So, we've got some sort of summary statistics here, but effectively you're saying even though at their flow extrema, they're relatively similar, but the sort of median flow, that there is variability, with the Kilburn arguably being the most connected to its subsurface aquifers. So how can we look at this in some sort of chemical transport? So we've looked at fluids, we've looked at how they're connected to the subsurface, but what are they doing to the sort of transport and mining related substances that we might want to detect? So we've calculated the flows before, and then through the field study that we've done with the chemical monitoring, we've been able to sort of quantify, say, in terms of iron, that we can see in absolute terms there's about, sort of between 2 and 100 kilograms, 150 kilograms a day of total iron. So that's including particulate iron in the bed sediments that's been remobilized. But obviously that varies quite significantly with the overall regional flow, because we're not always talking about the low flow conditions. We are maybe doing the summer, but obviously in winter we're sort of winter and the autumn we're into higher flow conditions. But despite that flow variability, the iron is only maybe is maybe sort of oh sorry, that's the dissolved iron is up to 10% of total iron, and then we can do the same for manganese. But what we're interested in is how much. Oh, sorry, that animation's gone the other way around. The kilburn, sorry. Obviously, we were saying it is interest before because it's quite intimately linked to its underlying aquifer, and we'll see some more evidence for this in a minute. But what we're actually saying is when the Bilston joins the North Esk, up to potentially all or half to all of the dissolved iron that you record at the Bilston confluence could potentially come from the kilburn. It's not necessarily a conservative solute, but at least it sort of gives you an indicative saying that the magnitude is at least half of what ultimately ends up in the North Esk at that point.
Just a 5-minute warning there, Sam.
Oh, heck, right, okay. And then the final thing to take on is the amount of iron leaving this Bilston Kilburn catchment across flow is potentially is around 10 to 20% of the iron downstream of that. So there's still 80 to 90% that we need to account for somewhere else, which I'll get to on in a minute. So again, how is this interacting chemically with the system? So we can take the idea of a Younger plot, which just sort of allows us to sort of chemically characterize our groundwater into sort of different mining related facies. And then when we do this, sort of taking the summer nominally, we find actually most of it, even in the rivers, do sort of plot in the river freshwater, even though there's a mining hinge to it from what we see in the mass balance. But the Kilburn plots nicely over into the shallow ferruginous mine water, which is also the one that we saw before has a strong relationship to the to its underlying base flow component. And this is sort of just a sort of map of summarizing that for those who want to take a bit of time after on the video to sort of see where those hydrological facies work in a sort of more conceptual system. So the last thing I'm going to try and rattle through, given that I've only got about 5 minutes, is a sort of idea that I've come up with to sort of say how would we potentially detect if something was going wrong in the system. And say we've got a fault, which we'll see in a second, cuts the river, and then you've got some water leaking from the mine workings up that fault into the river. Downstream of that point, the flow is equal to basically the flow from the river plus the flow up the fault. And what we can do is measure the physiochemistry at that point. And then obviously if there was a leakage, it would move that distribution of physiochemical properties by some amount. So we can compute that delta by looking at sort of the difference in those time series upstream and downstream of the fault. Then the question is, well, what perturbation in that would we need to make that observable to us to actually say, has something gone wrong? So it basically amounts to a sort of hypothesis test of a non-Gaussian problem. So we can use a Mann-Whitney U test to do this. And basically, we basically use this to progressively work out what delta we would need to get that there is a change at a certain degree of statistical significance. And we're going to take this example of where we do see the reduction quality of the water decrease downstream of a fault. So in other words, we think there is something potentially already happening here. How much more would we need to identify a problem on top of that in an operational scheme? So we run this for oxidation reduction potential. We find it's 7.8 millivolts, pH nearly 0.1 of a pH unit, conductivity 3.6 sieverts per centimeter, and the temperature's 0.1. So the question is, how much do we need to get that change? And I promise I've only got one more slide after this, Gareth, just to wrap up. But we can again sort of do a mass balance calculation on that to work out what fraction of the water is contributed by the fault, which we can get, and as I'll show you in the next slide, we will get that from a sort of Freak-C-based chemical mixture model, and then we can get the river flow from the flow duration curves from gauging stations. So if we run this as a nominal example for pH, we've mixed the sort of river water at the point where the fault and a sort of Bilston Glen Old Fordell type mine water chemistry and worked out what that mixing would do to the pH. And we know for pH that we basically, from what we saw before, we can work out what fraction of mine water we would need to mix into the system to nudge those distributions by the amount that we would need to make a statistical observation that something's got wrong. And we find that actually for temperature, it's 10 times the value that we would need for conductivity or pH, which ironically suggests that temperature might not be a great proxy to use for this, because more's got to go wrong for you to notice this. So if we do this for sort of nominal median flow, we can work out how much mine water we would need to leak for us to potentially find that something's gone wrong. And we find for pH and conductivity, we can actually get sensitivity about 4 litres a second up the fault would be enough on a prolonged basis to detect that, whereas you'd need potentially 10 times that for the thermal breakthrough to be detected using that as a proxy. Obviously, the question is then how long would this leakage need to occur for us to actually make the detection in the series? That's sort of some ongoing work. And then I'll put up the sort of summary slide there, but I'll happily take any questions